Welcome to Earlsdale Retreat. A previous video, Introduction to Eco-glamping, gives an overview of everything I hope to achieve, and I'll include a link to this video above. If you find the ideas of these projects as exciting as I do, please subscribe and click the bell icon to be notified of future videos. This video is the second from a series about improving water quality. The first video focused on monitoring dissolved oxygen, commonly referred to as DO, which is the single most important water quality indicator, and showed how different fish species can be impacted by changes to dissolved oxygen. In that video, I showed how the oxygen content of the water was lower than I would expect from spring-fed water. This could be a serious problem. I might influence what fish I stock and might potentially delay opening the fishery because of all the work involved with understanding what's happening and how to put it right. All of the videos can be watched in the playlist Birth of a Fishery. I've repaired a boat that we rescued from the pond after it had sunk. We made a boom to remove excessive duckweed from the pools, and we opened up air pathways by removing invasive rhododendrons. To build up a picture of what's going on, I need to know what's causing low dissolved oxygen. This video focuses on measuring water parameters, and I'll try to explain why these parameters might be having an impact. Whilst I take a sample for the first measurements, let me explain. As DO fluctuates, so too does carbon dioxide, referred to as CO2. When CO2 is dissolved in water, the release of hydrogen ions in carbonic acid lowers the pH. Water of lower alkalinity can lead to marked pH fluctuations throughout the day, accelerating the release of metals from rocks or sediment. These metals can affect a fish's metabolism and their ability to breathe. At the other end of the scale, at a pH greater than 9, most ammonium in water is converted to toxic ammonia, NH3, which can be fatal to fish. This chart shows the ideal range of pH. As you can see, the acceptable range is between 5.5 to 9. Values below 7 are considered acidic. 7 is considered neutral, and above that is considered basic. Trout thrive in water with a pH in the range of 6.5 to 8, whereas carp thrive in waters with a pH of 7.5 to 8. To get a really accurate result, I would like a photometer, but these are really expensive, so I'll have to make do with a pond testing kit, obtained from a local aquarium. This kit consists of strips, which measure various water parameters, including how hard the water is. It also measures nitrate and nitrite, but I'll ignore these results because I'll use a more accurate measuring kit, which is more suited for measuring low ranges of nitrates. The strips included in this kit change colour when activated, and can be compared against the chart included on the package. Water hardness is split into two measurements. Carbonate hardness, or KH, measures the amount of carbonates and bicarbonates in water, which affects the buffering capacity of the water. This means that KH helps to neutralise acids, preventing wild swings in the pH. High KH means that the water has a higher buffering capacity. The measurement of KH is usually referred to as parts per million, and ideal conditions would be in the range of 70 to 140, but the test kit measurements are in German degrees, so I need to divide the ppm by 17.9 to give me a reference to this test kit. This would give me a range of 3.9 to 7.8. General hardness refers to the mineral content of the water. As water runs through mineral-rich rocks such as limestone, the minerals are dissolved into the water. The term for water with little mineral content is soft water, and some fish, such as carp, thrive in waters with a high mineral content, as long as the hardness comes from calcium and magnesium, which help the fish to create new bone tissue, scales, blood clots, metabolic reactions. In soft water without calcium, the fish would have to use higher levels of energy to replenish lost salts within the blood, which can lead to less growth, weak bones and frequent illness. Harder water can also help the pond's buffering capacity to withstand fluctuations to pH, which is what I'm most interested in here. What I'm hoping for is a general hardness around 130 to 195 milligrams per litre, although I would accept readings up to 250, which most freshwater fish can quite happily cope with. The test strips again measure in German degrees, so I need to divide the ppm range by 17.9 to give me a reference to the test kit. This will give me a range of 7.2 to 10.9 German degrees. So armed with this information, let's take a look at my results. You can see that the pH is somewhere in the region of 7.2 to 7.6, so spot on ideal conditions. The carbonate hardness is between 6 and 10, towards the limit of the ideal range, or possibly just above. This should provide a great buffer against wild swings in pH, and I'm quite happy with this. The general hardness is somewhere between 7 and 14, and probably closer to 14 than 7. This is slightly higher than the ideal range, but again it's within the maximum acceptable limit of 250 parts per million, so I'm happy with that. In conclusion, I'm happy with these initial results. Now I have to explore what's causing the prolific growth of duckweed and Canadian pondweed, and ultimately solve why I'm getting low dissolved oxygen readings. I already have a good idea of why. I expect the pool is experiencing eutrophic conditions. So what is eutrophication? I'll try to explain with these slides. So you have a pool stocked with fish. Any number of things can influence this body of water and introduce an undesirable level of nutrients. Perhaps you stock too many fish, in which case the sheer biomass exhausts the oxygen, whilst the poop and fecal matter causes high ammonia, which has a direct toxic effect on aquatic life. Intensive agriculture is also a major issue. Runoff caused by years of over-fertilising fields with enriched phosphates to accommodate too large a biomass of animals, or allowing slurry tanks to leach into the ground is a major cause. This can wash into bodies of water, causing an influx of undesirable nutrients. Too many trees around a body of water can cause leaf matter to settle at the bottom of the pool, creating silt and containing a high biomass of organic matter. As this silt breaks down, it releases nutrients into the water. Old and leaky septic tanks or a poor maintenance regime can be another contributory factor to nutrient enrichment. If the fecal matter isn't properly dealt with, heavy rain can wash this into streams, rivers or pools. And don't even get me started on the illegal dumping of raw sewage by UK water companies. For example, the Environment Agency found that 7 water firms oversaw an increase in serious incidents last year compared with 2020, with the highest rate of serious incidents since 2013. Over time, all of these factors cause high levels of silt to develop and releases even more nutrients into the water as the organic matter is biologically broken down. On sunny days, these nutrients can lead to algae growth. Planktonic algae can be beneficial to aquatic life forms as a rich source of food. However, the algae growth can become very severe. During prolonged sunny periods, the algae can cause supersaturation of the water. That is very high concentrations of dissolved oxygen, which can lead to gas bubbles forming in the blood of aquatic animals and lead to stress or mortality. Whereas algae and plant life provides oxygen during the day through photosynthesis, during night they respire, taking oxygen from the water and releasing carbon dioxide, which, as I said before, forms carbonic acid and increases the acidity of the water. Dissolved oxygen can fall to dangerously low levels, causing stress and potential mortality to aquatic life. Prolonged cloudy days following extended periods of sunshine can be even worse, killing off the algae bloom and further exacerbating the problem. Because aerobic nitrifying bacteria multiplies to break down the dying organic matter, and again this consumes oxygen from the water, until only anaerobic bacteria exist. That creates anoxic conditions at the bottom of the pond, where water is devoid of oxygen. This can also lead in a turnover event where you suffer a total collapse of dissolved oxygen within a very short period of time. During thunderstorms or heavy rains, the cooler water sinks to the bottom of the pond and mixes with the warm, deoxygenated water. This sudden mixing can shock the fish, causing total mortality. This is what's known as a fish kill event, and this is why we really need to focus on improving our water quality and look for ways in which we can prevent further deterioration to our waterways. After all, we all rely on water, not only for our own consumption, but all life forms on the planet. And my pools are at the head of the watershed and the spring fed. The water from these pools travels into a brook, which then enters a major river. If we can't trust the water quality at source, what hope is there for anything downstream? If we continue on our current course, pretty soon the damage will be irreversible. This is why I want to explore alternative waste management, things like using compost toilets, grey water reed beds, but that's a topic for another time. So let's focus on the pond water quality for now. To recap, I now know that the water basics are okay, but we need to find out if the water suffers from high nutrient concentrations, leading to eutrophic conditions. To investigate this, I will use another kit that accurately measures low range of phosphate and nitrate. To measure phosphate, I'll start off by assembling the comparator, which has a central dial with various colours representing the levels of phosphate. Using a syringe, I'll dispense 17 milligrams of water into both vials, and the first vial will be placed in the holder in the outermost position. I'll then dispense 13 drops of reagent A into the other vial, apply the cap, give it a good shake. I can then add 4 drops of reagent B using a squidgy thing, and again give it a good shake. After 15 to 20 minutes, the colour can then be compared to the comparator. Now I found the water to be a light green colour, registering somewhere between 0.1 milligrams per litre to 0.12 milligrams per litre. The ideal phosphate level should be in the region of about 0.05 milligrams per litre. So my measurements are a little high, but actually not as high as I expected. This could be because the phosphate is locked up in a prolific plant life. If I allowed this plant life to die off without removing it from the water, it's likely the phosphate levels would spike, and these results could be much higher. That's why I'm concentrating on removing the Canadian pondweed with rakes and extracting the duckweed with a boom. This removed biomass should also make fantastic compost, rich in phosphate. Nitrates are measured in a similar way. The comparator dial is just turned over to measure nitrates instead of phosphates. The reagents are applied as instructed, and then again it's a matter of waiting. What I found surprised me. The vial was almost clear, with a very slight tinge of pink. The measurement was somewhere in the region of 0.125 milligrams per litre, maybe even less. And this is actually low, suggesting that all available nitrates have been taken up by plant life. Perhaps by limiting the nitrates, I will be able to control the eutrophication. But first I need to identify where the phosphates are coming from. This will be dealt with in another video, where I'll show the dissolved oxygen changes over a period of time, and any changes that I find with the nutrient levels. By measuring different points of the watercourse, I also hope to identify where the phosphates are higher, and therefore how they might be entering into the pools. If I can find this out, I can then come up with a management plan to tackle the problem. So if this might be of interest to you, subscribe, click the notify icon to be informed of future video releases, and I hope to see you again. Bye.